Hello, I am Julian Cobell, and welcome back to Lawrence Berkeley National Laboratory's instruction video course on laboratory testing of Cookstove. Today's lesson is on the design of the laboratory ducting system. In the previous video, we went over the design of a testing hood that completely captures emissions generated by a biomass cookstove. The ducting system safely exhausts all emissions to a chimney outside the laboratory. Furthermore, the duct provides a well-mixed stream of all cookstove emissions, making the duct the logical location for emission sampling. A good ducting system will 1. Provide enough flow to completely capture the emissions in the hood, 2. Be free of any leaks that may allow emissions to escape into the laboratory or allow laboratory air to leak into the duct, 3. Provide fully mixed, fully developed, turbulent flow for sampling, and 4. Provide an accurate measurement of the volumetric flow rate of air passing through the duct. The ducting system consists of a circular steel duct commonly used in building construction for heating and ventilation. The International Standards Organization recommends that ducting sections have a diameter ranging between 10 and 30 centimeters. In our laboratory, we use ducting between 15 and 25 centimeters in diameter. Ducting sections are joined together to connect the testing hood to an inline, squirrel cage type blower. The ducting sections are sealed together using an aluminum-backed tape. This tape should be regularly inspected to ensure that there are no potential leaks at the seams. As the blowers pull air through the duct, it first passes through the hood and then through a long mixing tunnel. It then passes the sampling port, a flow measurement device, and finally is exhausted through the blowers and out the chimney. In addition to just moving air through the duct, the blowers must satisfy two important criteria. First, the blowers must induce a face velocity on the hood that is high enough to fully capture emissions, but not so high to induce a draft on the cookstove. Second, the blowers must draw enough air through the ducts to induce turbulent mixing. This turbulence will help completely mix clean room air with cookstove emissions. Both the hood's face velocity and the turbulence in the duct are controlled by volumetric flow rate of the blowers. As discussed in a prior video, the volumetric flow rate through your duct should not induce a face velocity higher than 0.25 meters per second at the opening of your hood. While it is good to reduce face velocity to minimize draft, it is also important that all cookstove emissions are captured and well mixed with ambient air. For this reason, there is a combination of considerations between hood opening, duct diameter, and volumetric flow rate. In our lab, we use a volumetric flow rate of 325 meter cube per hour, with a hood opening of about 1.5 meters squared, giving us a face velocity of roughly 0.06 meters per second. For our open bottom hood configuration, we find this face velocity is sufficient to capture all emissions, and we therefore recommend that the face velocity in your system be maintained above roughly 0.05 meters per second. While the volumetric flow rate should be low enough to prevent draft, it should also be high enough to ensure complete mixing of the emissions and room air. This is because the emissions are sampled from the duct, and we want to ensure that a sample taken from the duct is fully mixed and not biased towards polluted emissions or cleaner room air. Sample probes for emissions instruments, such as gas analyzers and gravimetric filters, are mounted inside the duct using an access panel. In order to ensure that the sampled flow from the probes is fully mixed and representative of the emissions generated by the cookstove, the flow in the duct must be turbulent, fully developed, and fully mixed. To achieve these conditions, the International Standard Organization recommends that 1. The Reynolds number of the flow be at least 10 to the 4th, and that 2. The sample probes be mounted downstream of a straight ducting section with a length that is at least 8 times the duct diameter. In the commissioning, calibration, and verification video, we will discuss how to verify that the emissions in the duct are well mixed. However, well mixed exhaust begins with good duct design. We recommend that the straight sampling section of the duct be connected to a hood using a 90-degree elbow. Given a duct diameter of 0.15 meters, the recommended length of this straight duct section downstream of the elbow must be at least 1.2 meters. Similarly, if an elbow or other restriction is placed downstream of the sampling probes, we recommend installing a straight section of ducting with a length of at least 4 times the duct diameter in between the probe and the restriction. This straight section will help prevent the restriction from creating any disturbances in the sample flow profile. With these flow conditions, the instruments can measure a representative sample of the cookstove emissions and can output accurate concentration measurements of CO, PM, and other pollutants. The measurement of the volumetric flow rate through the duct is typically accomplished using a differential pressure device. Several instruments are suitable for this application, such as an iris, pitot tube, or flow grid, but we have found that irises are reliable, easy to calibrate, resilient to soot buildup, and accurate. Consequently, we recommend using this method and implement it in our own lab setup. The iris is installed downstream of the sampling probes and upstream of the blower. The iris must be exposed to a fully developed flow profile in order to output accurate differential pressure measurements. We recommend installing straight ducting that is at least 12 times as long as a duct diameter on either side of the iris. Given the dimensions of our lab, it was not possible to fit a single, straight length of duct with the requisite distances between the hood, sampling probes, iris, and blower, as shown in this diagram. Consequently, we installed a 180-degree bend in the duct to separate the straight ducting for the sampling probes and the straight ducting for the iris. By installing the iris or other flow measurement device in this manner, accurate differential pressure measurements can be obtained. The differential pressure generated can be measured using an analog gauge, or logged electronically using a pressure sensor. Differential pressure measurements are then converted to volumetric flow rate using techniques that we discussed in the video titled Commissioning, Calibration, and Verification. Here is a summary of the ducting system design principles that we discussed during this video. 1. The blowers must generate enough flow to completely capture emissions from the hood into the ducting system. 2. The ducting sections must be carefully mounted and sealed using aluminum tape to prevent any leaks into or out of the system. 3. The ducting must incorporate uninterrupted, straight sections to ensure that instruments sample fully developed, fully mixed turbulent flow that is both consistent and representative of the emissions generated by the stove. And finally, 4. The ducting system must incorporate an accurate and reliable volumetric flow rate measurement device. Thank you. I'm Julian Cobell from Lawrence Berkeley National Lab, and join us for our next instructional video on laboratory testing of cookstoves.